this is not a closed form. So this is the people have done a lot of experiments and they just do some processing the best fitting to get that equations. So I also taught you the stress, strain, and the displacement. Can somebody tell me among these three quantities, which one is not singular and why? And which one is singular and why? Okay.
I know stress is singular because it's 1 over the radius. So if the radius goes to 0, the stress goes to infinity.
Because stress is proportional. This sign is proportional.
Yes.
1 over square root of r, right?
Yeah.
So when this r approaches 0, so this value will be infinity, right? So when r goes to 0 and this one blows up, that's the reason this guy is a singular. Also epsilon. And usually epsilon and sigma, and what is the relationship between epsilon and sigma? The only relationship is the material properties, right? The material properties bridge the gap between epsilon and sigma. So because sigma is singular, and this guy is also singular. However, the displacement is not singular. Right? Can somebody tell me, Bobby, what is the relationship between this is U with respect to R?
Is it just the square root of r? Or yeah.
So say this guy is a numerator, and this is R goes to 0, and your displacement will be 0. This is totally fine. However, for these two guys, when R goes to 0, these two guys will blow up. That's the reason singular. And when we talk about this is the numerical methods or these mechanics, and we will hear often the singular. Whenever you hear singular, you know the denominator almost 0. Okay? You understand that? You can see U is okay. U is not singular. Why? Because when R goes to 0, U will just go to 0. It's okay. But these two guys, when these two guys go to 0, so these two guys will be infinitely high, which is impossible. Okay, so this is what we have learned last time. Now, today we are going to continue our talk. I will give you several equations for commonly used specimens. First, so for this one, okay, this equation I told you K sigma ij is described by using Ki 2 pi r. So you can see sigma is a function of 1 over r. So here is the function. This can be a very is a complex function. And so you can see the unit of Ki it equals stress square root length. So the international unit is Pascal square root meter. Okay, guys? As I always say, our mechanical engineers or aerospace engineers, the units play a very, very important role. Whenever you do something, you cannot just give people a quantity. What is unit? Unless this guy is unitary, dimensionless, or just this guy just ratio. You guys agree? But we need to keep this in mind. The stress intensity factor, this guy's standard international unit is Pascal the meter. And for we can just have this is this US customer unit also, right? You can see Ki is definitely is proportional, is a function of sigma and how much stress you are applying, and also at that instant how big the crack is. So this is a function of these two guys. So we know Ki is proportional to sigma square root A. This global analysis is needed to determine the coefficient. So this one for any linear elastic problem, so this equation holds. But what is exactly the coefficient is, that's another story, right? So qualitatively, so this equation is always true as long as linear elasticity is assumed. But what is exactly the coefficient is, it depends upon the configuration of your specimen. We're going to talk about this one. For example, for through thickness hole crack in an infinite the weld plate subject to the remote tensile stress, for this guy, we have suppose, okay, practically it's impossible, but theoretically it is. Infinitely the bigger plate, we have a through hole. This hole goes from this side to the back side. So we suppose we have this is a remotely applied load, and we also know the thickness. And so this Ki is coefficient equals 1. So this is very, very beautiful standard equation. But for the semi-infinite plate, and for this one, I just cut it in the middle. Okay, cut it in the middle. For here, I just this finite. This is the finite. This is edge. But for all other three directions, infinitely big. But here, the crack, half crack, still have remotely applied load. And for this one, we have a unit that is a little bit higher than the unity than 1.0. So this is for for edge crack, for the edge crack. The third case scenario is the penny-shaped crack. A penny-shaped crack for this one, infinite dimension in all three directions. But here we have is a penny crack. This penny crack's radius is given is A. For this guy, we have so this equation. You can see the coefficient here is a little bit lower than 1.0. Understand, guys? One more time. How did the people get this coefficient on the doing experiments? They measure. Understand, guys? Okay, so this is for these three cases, for these three equations, and our assumption is that the direction of the applied load is perpendicular to crack face. So this is the three equations, and the underlying assumption is that the applied load is perpendicular to the crack face. And however, we know practically, and we can run into a lot of other problems. For example, if the crack, the face is not perpendicular to this is applied load, and what we can do, and we can use this is Mohr circle, either Mohr circle or this is a mathematical representation to do the stress transformation. You guys still remember how to do the stress transformation, guys?
A little bit. Mohr circle.
Yeah, Mohr circle. Mohr circle is a graphical representation. We have three functional equations for the 2D problems, right? For 2D problems, and for this, whenever we have this problem, you can see this is the whole, but the sigma, suppose the sigma not go vertically, but go this direction. What we should do on this is the third crack face, we need to do the stress transformation. Our goal is to get vertical direction, the stress in vertical direction about this surface, and also the tangential direction about this surface. Because for the opening, for the mode 1 opening, only the vertical components make sense, right? However, for the tangential one, what will happen tangential? For the tangential one, that is mode 2, is sliding. You can imagine, right? For the mode 2 as a sliding. Look at it here. For this is the sigma, and for this is we can do the stress transformation, and this is sigma and stress transformation and usually goes this way. So this is the x, so this is a y, and you have the sigma, this is sigma tensor. And then if I change the direction, so make sure this is x prime, and also this is a y prime. So this is the theta, this is the orientation, the theta value, and also this is the theta value. And you can do the stress transformation and either using this Mohr circle or use this mathematical equation. So here is a mathematical equation. So here is a mathematical equation. So in the x direction, we have this. Suppose this is rotate beta, okay? And here that is in this figure we are using beta. It does not make any difference. Yeah, just the beta. And for this is the in x direction we have sigma cosine square beta. So this is our tau y prime tau y prime. Tau y prime is in this direction. Sigma y. And for tau x prime y prime in this direction, which is a shear, right? And for the model 2, we have this equation. So we can have Ki equals, and still this is a sigma, right? This is a sigma pi A, and the K2 is sigma beta cosine beta pi A. So this is first mode, this is the second mode. Or here, you can see this. This is my sigma. But suppose this sigma is not perpendicular to the crack face. What should you do? You should calculate the new normal stress, the new shear stress. So you can see we just tilted a little bit, and we have this is a sigma yy going up and sigma y prime x prime shear. So this shear, this one and this one, these is two shear couples, and will generate the mode 2, the crack propagation. So this is sigma y prime. So this is stress couples, and they will have mode 1 opening. You understand, guys? Bobby.
So like in the case of A, where you have a load that's not perpendicular to the crack face?
Yeah, this is original one.
Okay, so that's causing mode 1 and mode 2, like both of them.
Yeah,
Okay.
this guy is our original configuration. Okay, when we analyze it, we need to use this because these equations, the underlying assumption I give you for these three equations means that the sigma is perpendicular to the crack face. But now the sigma is not perpendicular to this crack face, right?
Yeah.
And what you should do, you should decompose this sigma into normal direction and also into this tangential direction with respect to the crack face. So whenever I talk about crack face, this is a crack, okay? So this is a crack. So suppose this crack is very sharp. So this surface and this surface, mathematically, I can say they are identical. So this is a crack face. This is what I'm talking about. This is my crack face. So this is a crack. This is a crack face. Questions so far? You can see when this crack face is not perpendicular to a sigma, and you will have both Ki and K2. And how to calculate using these two equations? I hope you guys follow me very closely. If you follow me very closely, our class, you don't need to spend your time, more time. Questions so far? Look up here. So here are the two case scenarios. So here, this is the embedded crack. This is a surface crack. You can understand this one, right? Huh? You understand this? So this is embedded the crack. So this is only the half crack. We have a surface there. And for these two cases, And so this is edge. This is edge surface. So this is edge surface. We only have a semicircle. But here is a full. We do not call circle elliptical. So for these two cases, and we use this KI. Use this calculator KI. And KI equals sigma. You can see it's a function of sigma and also A. But here lambda s, q along with the function f, and they are given here. Q using this equation, lambda s function is here. And what is the phi, guys? And phi is orientation. Okay. Phi is orientation along the crack tip. Questions so far? The A is the dimension in one direction. C is the dimension in another direction. This is kind of small. I just rotate it here. So then we take a look at effect of finite size. Effect of finite size. For this case, guys, we just think we have a crack, but we think it is very, very wide. Right? Wide, it's infinitely wide. But for this one, the same crack, but we know it has finite width. And for these two case scenarios, and we can get, so this for this KI, and for this KI is for this, and for this B, finite plate, and for the finite plate guys. We usually have finite plate. So this one and just give us shows infinite. You can see so this guy and this guy is different. Do you guys sense the difference? You can see here. You can see here is still very, very quite straight. These two equations are for this finite widths. And this one, what's the difference? So this one, the second one is more accurate. It is obtained using the FEM. Can you write down? Equation 2.46 and is more accurate, and it is obtained using FEM and finite element method. So here is a comparison of these two equations. And for this is the finite plate and with finite width of this this is a crack. So what the bottom line is that if we have geometry and apply load, and you can come here and to use the appropriate equations and to get the KI. Okay, so this is my bottom line. And how to derive this is not required. If we want to learn how to derive this, we spend another year, 1 year to learn. That's not. But for our mechanical engineers or these aerospace engineers, our goal is to use this to solve our problems. Understand, guys? How to derive it? That is the job of mechanics people or the mathematical people. Do you agree? We just use what they give us to solve our engineering problems. That's the difference between science and engineering. Right? What is the difference between science and engineering? Science gives us the principles, how it works. Right? Engineering job is for some work that is beneficial for us, for our society. We created some useful products, services, and to better our lives. This is my understanding. Maybe yours is kind of different from yours. Okay, so here this is a table. And you can see this table is very, very beautiful. Right? The KI solutions for common the test specimen for this sand, single edge notched tensile, with this, the parallax and applied load, and we use this equation to calculate, this is a KI. We use that equation. Right? We use that equation. And the single edge notched band. So here is a crack, edge crack, but we have the point. So this guy is also called 3-point bending. Right? You guys agree? 3-point bending. We also have a 4-point bending. And we also have three bending. We have 3 different commonly used bending. One is 3-point bending, second one is a 4-point bending, and third one is a free bending. So next one is the central cracked tension, and called CCT, central cracked tension. Next one, double edge notched tension dent. So for this guy, is located in the center, and we have a P here. So this equation is the F equation we are going to use to determine our KI. So you can see this is KI, okay? And KI for here we use a P. We are not using the sigma. And P, KI equals P, B is width, how deep it is. And the square root of W, FAW. And this one guys, I want you to familiarize yourself with this one. Why? Because we are going to do this and we are going to model this guy in our quiz 1. Alright, Bobby.
The crack, the big black line, is that the crack and then
The crack.
Is okay.
This is a crack. Yeah, this is a crack. I want to say that's a good question. So we assume the crack is very sharp. The crack is very sharp means that this is a crack surface, this is a crack surface. So mathematically, we can just assume these two guys are identical to each other. Okay? Identical to each other. The very, very sharp crack. Not this way, not this crack, but very, very sharp crack. You have sense?
Are they all like through cracks? Does that matter? Or
The
like...
through crack. For all these cases, they are through crack. That's a good question. Through crack. For all these specimens, for all these examples, we assume through crack. Through crack means that this guy has a thickness, and this is through this is thickness, this crack. That's the depth of the crack. So I want you guys to keep in mind this one, to pay more attention to this. And also, when we build the FEM model, guys, okay? Look at me, please. When you build the FEM model, because the symmetry, we only focus on either upper portion or the lower portion. Can you write down this? And we only focus on either upper portion or lower portion because of the symmetry. And we just imaginarily create a line, and we just apply boundary condition on this segment, on this ligament, and then we focus on this part only. You understand? But the displacement of this crack tape, and finally will be doubled by 2. Because here is 1, that is 1. It will be doubled by 2. Do you agree, Bobby?
Yes, right, because it moves up.
Yeah.
This.
So this part moves up.
Yep.
So this part moves down.
Yeah.
Same amount of displacement. That's the reason we have double 2. Yeah. So read some comments here because as I said in our quiz 1, we will focus on this specimen. So here this plot and this plot show different the function f, which is a function of a over w, and for different specimens. So here is the one statement. If you have taken machine design with me or say computer aided engineering with me, you should be familiar with this equation, right? I hope. Let's remember this equation. So this is y is called y or lambda. Sometimes we use lambda. Y is called imaginary geometrical correction factor. Depending upon what kind of loading are you applied and what kind of geometry of your specimen. So y is called dimensionless geometrical because it is based on geometry of specimen. Correction factor. And then we talk about the principle of superposition. So even though we have learned this one either computer aided engineering or machine design, but here I want to talk about this one in the context of the fraction mechanics, right? So the same thing, but in the context within the context of fraction mechanics, and we use different examples to illustrate. As you can see, this assumption for linear elastic material. So this assumption must be met. Okay, otherwise this superposition principle is not accurate. You understand? So this one must be satisfied first. You can see for linear elastic materials, individual components of stress, strain, and the displacement. So these three guys are called solutions. Whenever you have a problem domain and functional loading conditions on the boundary conditions, the solutions means that we know how to describe displacement, how to describe the stress, and how to describe the strain. You guys agree? So that is the solution fields. So individual components of stress, strain, and displacement are additive. It means this way, okay? It means here is a load one, and suppose for load one, only load one, I have Ki for load one. So this is for load one. For load two, only load two. No load one, no load three, only load two. If you apply load two only, and you can have Ki2. And the same thing for load three, and you have Ki3. It means that, okay, when you apply these three loads together simultaneously, and you Ki total will be the addition of these three guys that you obtained by individually apply each of these loading condition on the specimen. You understand, guys? Dylan, you understand? Yep. Okay, and however, Ki total is not equal to Ki, K2, K3. If we want to do the superposition, they must follow the same mode. Understand? Okay, here. That is example is a good example. Another example is this. And I have the same principle. And so for this one, suppose this is a specimen, same specimen for the three conditions. And for first condition, I apply the remote load P. So this guy's result will be equal to, first, I have, this is a lowercase p, just near is a crack, just on the crack, in the neighborhood of the crack. So this is one condition. And second condition is that I have the P, and I also near the crack, I have opposite p, opposite lowercase p. So this case equals the addition of this one and this one. You understand, guys? Why this one is important? Because in later in the future, we can see as long as I have the remotely applied load, I can use this superposition principle and to focus on the load here. You can see and KIA here equals KIB and plus and the KIC. So KIC, here is the P, and here is also the P, and these two guys cancel each other. But it equals, it does not matter where you apply the P. This is what I want to say. Hey, Bobby.
It's the same P, like it's not like big.
Yeah, same P,
Oh,
same P. Okay, here is the same P. This is the same P. You can just treat this one as a lower P or lower P. This one will not be equal to 0. Right? But they without loss of generality, you can here we can have the same P. And same P, this one cancels this. But this one equals this. It means that it does not matter where you apply the load. So this is the conclusion what we will come, what we want. You can see the stress intensity factor for internal loading equals stress intensity factor for remote loading. So this observation is very, very important because we are going to use this one a lot. Let's see, okay? There is one thing. The stress distribution is the same near the crack, but at a different far away from the crack. Make sense? So this stress field only the same near the crack, but for the area far away from the crack, they are different. Understand, guys? Questions so far? So you can see that this one, okay, this one is more general. Right? For this case, so this guy still equals this one, but here I will not use the same one, but I use another one. You can see?
Yeah.
You can see here, okay, if Px is not uniform, so P is not uniform, and for C, assume no crack and phase the traction Tx, then this Tx should be the one applied on the B. Suppose there's a no crack. So this Tx and fully cancel this one, and you need to calculate the T on the plus Tx. So then we talk about the weight function. The weight function can say this way, okay? This is the weight function, and we use this is the use this one. This is the weight function, this algebra. And for this load 1, we have K1, Ki1. And for load 2, we want to calculate the Ki2. And how can we calculate the Ki2 based on the Ki1? So Rice, the professor Rice, and showed that Ki1 and Ki2 and they are related using this equation. Right? Follow me, please. Follow me. So Ki2 equals E prime, and E prime is effective Young's modulus. It is dependent upon whether it is principal stress or principal strain. So this is Ki1, and within this square bracket, we have this is a boundary gamma, Ti2, okay, and Ti2 the boundary. So this is the boundary, practice boundary. Ti2 and DUI DA is 1, okay, for the first one, and you already know D gamma, this is D gamma. The Ti, I'm sorry, this is T, I will use a T, but the gamma is along the gamma. So second one is Fi, the body force. Fi is body force for the two, for the unknown condition. DUI for first one with respect to A is area. So this equation, and based on this equation, we can calculate the Ki, and based on the Ki1, Ki2 based on Ki1. So there is a the Ti is the surface traction, and the gamma is all boundaries and the cracked surface, all boundaries, and the Fi is the body force in each direction, body force, and Ui is the displacement in each direction. So here, there is a weight function. The weight function is defined as Young's modulus 2Ki1 DUI1 and dA. This is superscript 1 means the displacement or the Ki for the first loading condition. So it is equals this one also. This xi represents x and y coordinates. X1 means x, x2 means y. So there is only if there is only internal traction, guys, look at here. If there is only internal traction, that means on the crack tip, on the crack face, there is no body force. So this term will be disappearing. We only have this one. So that's the this Ki equals Pix Hix d gamma here. Right? That Px is the traction, and this is Hix is this. So we can use this equation to calculate the Ki. And why we need to use this one? Because we can standardize. So this one with function will be standardized with function, and we can just use this standardized with function to calculate the Ki for any loading conditions. So here is one example, guys. I want you to take a look at this example. So this example has different the form from the examples we show in the textbook. Why? Because in the textbook, you guys look at me, okay? Otherwise, you guys will be confused. In the textbook, we have a crack. In the textbook, and they use, so this is the left crack tip as origin. We have X and Y. But here, to be simpler, and we use the center of the crack as the origin. So this is X, so this is Y. I have positive X, I have negative X. That's the reason, and we have different, this one is the same, but Uy is totally different from the form in the textbook. Don't be confused. As I said, because I'm using the center of the crack as origin. But in the textbook, the Dr. Anderson used the left tip B as an origin. That's the reason mathematically Uy is different. Physically they are same, but mathematically they are different. Okay? So Hx, here is Hx, and here is this is Hx is Kia. This is the Ki at point A for the first loading condition, Kib, Ki for point B at the first loading condition, and then you can have Kip when you apply P, and you have this one. When you apply P, you can have Kib. So I want you to take a look at this one. So this one will be very, very helpful for you to understand what is the weight function, and based on the stress intensity factor Ki1 and how to calculate the Ki2. So this is the example. Okay, guys, do you have any questions? No question? Without further ado, I'm going to end today's session. And so this Wednesday, I'm going to talk about our homework 2 at the very beginning of our class. As I said, it's the Friday, after you submit your homework 2, I will give you the quiz 1 for modeling. Also, by the way, homework 1 has been ready, right? I'm going to post my solution sheet for homework 1, and you guys can take a look. And for this for the third problem, dimensional analysis, yeah, if we wrote anything, I just give you full points. But there's a lot of things you are missing. One guy has done a great job. I forgot this guy's name. I think you. Also Bobby has done a great job also. Okay, I will post the solution online. You just take a look. Okay.
Is this chapter 2 that we're going through?
Maybe.
Or-
Yeah.
Yeah, like this.
Chapter 2. Yes. Well, okay, chapter 2.
Okay, that's.
Chapter 2, section 6.
Okay,
Yeah.
thank you.
Okay.
Set up a meeting tomorrow, like tomorrow. I don't know, maybe.
Yeah.
Then I'll send you the other Zoom.